In this video, we're going to talk about nuclear chemistry. What word does nuclear remind you of? Probably it reminds you of nucleus. And remember what's in the nucleus? Protons and neutrons. So when we're talking about nuclear chemistry, just picture the nucleus, because we're really talking about the changes that are happening inside an atom's nucleus. Now, previously we talked about isotopes. What is an isotope? An isotope is an atom that has different amount of neutrons, which then affects the mass number. And keep in mind that all elements have isotopes. And so in nuclear chemistry, we're talking about radioisotopes, isotopes that emit radiation. So radioisotopes are atoms with an unstable nucleus emitting radiation. When atoms have an unstable nucleus, they have all this energy built up inside that in order to let out the energy, the only way it can let it out is through radiation. I always give the example of a hot-tempered person. Now visualize that person and think about how much anger they built up inside, how much energy is being built up inside, and that when they release the energy, they might lash out at somebody or whatever it may be. What happens to the person after? Usually they calm down, right? Usually they're stable again. And that's kind of similar to these radioisotopes. They have so much energy pent up inside that they release that energy in the form of radiation, so that's a lot of energy going out. And then afterwards, their nucleus is stable, okay? Now, generally, elements with atomic numbers greater than 83 are radioisotopes, and elements with atomic numbers less than 83 have isotopes with a stable nucleus, but also have at least one radioisotope, which again means unstable nucleus emitting radiation. Now here are some examples of radioisotopes in our real world. Now we use radioisotopes in medicine. We use it for radio tracers to detect disease. We use it in PET scans. We use it to treat cancer. We use it in archaeology and geology. I'm sure all of you have heard of carbon dating. We use it in food. We zap our food with radiation to prolong the life of our food and also to get rid of some bacteria. And I'm sure all of you have taken an x-ray before, whether it's at the dentist or a doctor has taken one for you because of a broken bone. And also we have radon levels in the area. So in the US, radon just exists in our soil and rocks. A lot of us do radon testing in our homes, especially if you have a basement or if you live on the ground level. They want to make sure that radon levels are not too high. And the reason why it's a concern is because it's the #1 leading cause of lung cancer. And so we want to make sure that there aren't high levels of radon where you're living. And in Virginia, we're usually fine in our area. Here are some of the risks and benefits to radioisotopes and using radiation. Sometimes, we have to think about if the benefits outweigh the risks, right? So let's jump into what nuclear reactions are all about. So chemical reactions, which will be the focus for the rest of the year, involve a change of electrons, meaning the nucleus does not change. But here today, we are focusing on nuclear reactions, which involve a change in the nucleus, which means our protons and neutrons change. Remember that the number of protons in the nucleus determines the identity of an atom. And as these radioisotopes go through these nuclear reactions, the nucleus changes, meaning that the number of protons will also change. So what's going to happen if the number of protons change? That means the element itself will change. And we'll talk more about that later on in this video. Now this is a band of stability graph. And what this is showing us is that small atoms, which are considered any atomic numbers less than 20, are stable when the ratio of neutrons to protons is 1:1. Okay, and so that's what this red line is showing us. Okay, so again, atoms with atomic numbers less than 20, this is their neutron to proton ratio here. And then large atoms, so atomic numbers greater than 20, are stable when the ratio of neutrons to protons is 1.51 to 1. And that's what this blue line is showing us. This is called the band of stability. Anything outside of that, so more, if it's above 1.52 to 1, so in this area, that would be considered unstable. And there we have our radioisotope. So Henry Becquerel discovered that radioactive atoms undergo significant changes that alter their identity. Unstable nucleus lose energy by emitting radiation, and as the radioisotope tries to stabilize, it transforms into a new element. Now, Rutherford discovered the 3 different types of radiation: alpha, beta, and gamma radiation. So here's Rutherford's experiment. He has his radioactive substance inside this lead block, and these are electrically charged magnetic fields, so positive on top and negative on the bottom. And he shot the substance through, and he saw that some of the particles went up towards the positive, some of them went down towards the negative, and some of them went straight through. So what did Rutherford conclude from this? The ones that were attracted to the positive field are probably negatively charged. And that's what he called the beta particles. The ones that were attracted towards the bottom to the negative field were positively charged, and that's what he called alpha particles. And the ones that were unaffected and that went straight through said those are neutral, and those are called gamma rays. So let's take a look at each one of these particles. Now there are 3 types of decays that a radioisotope can go through. The first one we're going to talk about is alpha decay. In alpha decay, the nucleus emits, or it gets rid of, an alpha particle. An alpha particle has 2 protons, 2 neutrons, and a +2 charge. It is equivalent to a helium-4 nucleus, and therefore the alpha particle is actually represented by helium-4. Alpha radiation can be stopped by a sheet of paper. So you hold up a sheet of paper right up in front of your face, it can stop an alpha particle. This is an example of an alpha decay. So uranium-238 goes through alpha decay, and look at what happens to the element. First we had uranium. Do we still have uranium on the other side? No, because as uranium goes through this alpha decay, remember nuclear reaction, it means a change in the nucleus, which means change in protons and neutrons. And so uranium is not the same uranium anymore, but as it emits that radiation, it now becomes thorium. And this is how we know it went through alpha decay. It is represented by this helium-4 symbol, 4,2 helium. So the second type of radiation is called beta decay. Beta radiation consists of fast-moving electrons that have a charge of -1. It can be stopped by any thin piece of metal. An example of beta decay is the following. Here we have thorium, and it goes through beta decay, and it changes into a completely new element. And here the 0 - 1e is what we use to represent a beta particle. The last one we're going to talk about is gamma emission. Gamma radiation is just high energy that possess no mass and no charge. It usually accompanies alpha and beta radiation, and it accounts for most of the energy lost during the radioactive decay process. An example of gamma, for example, is X-rays. Because gamma rays are massless, gamma rays by themselves cannot form a new atom. It can be stopped by lead or concrete, which is what we see here. So you can see that alpha can be stopped by a piece of paper, beta can be stopped by a thin sheet of metal, and gamma can be stopped by concrete. So let's summarize and go ahead and fill this in your table. We have 3 particles, alpha, beta, and gamma. Alpha is represented by a helium nucleus, and go ahead and add this symbol onto your notes as well. We know that it's the alpha particle when it is represented by this symbol here. 4,2 helium. It can also be represented by this, which is just an alpha symbol. It's the Greek letter alpha. Beta are represented by electrons, 0, -1 e, or it can also look like this. This is the Greek symbol for beta. Gamma, remember, has no mass, no charge, and that's the symbol for gamma. It's like a diving fish or an upside down ribbon. Now this is how we recognize our radioactive decay. So I know we've gone over alpha, beta, gamma, so we'll go over it again. So here we have a nuclear equation. Polonium goes through alpha decay, and now polonium changed into lead, so the new element is now lead, and here is our alpha decay. Beta, we have carbon. It goes through beta decay to form the nitrogen atom, and here is our beta particle. Gamma, we have uranium that goes through the decay, and now we have thorium as our new element. And here is our gamma symbol, but also followed by alpha, right? And we know that because of this symbol here. Now let's go through two more types of radioactive emissions. We also have positron emission. So this is a positron, a particle with the same mass as an electron, but with the opposite charge. So you'll notice that it is the same symbol as your beta. However, here is our positive charge. So instead of saying 0, -1, it is now 0, 1. And again, this can be represented with an E as well, okay? Because beta and electron will be the same. Electron capture occurs when the nucleus of an atom draws in a surrounding electron, and it combines with a proton to form a neutron. So here we have mercury, and here is the electron. It captures the electron. So again, same symbol, 0, -1 beta or 0, -1 e. But notice that instead of it being on the right side where the products are, it's actually on the left side where the reactants are. So that's what the electron capture is, and that's how it's different from a beta emission. And notice again that the element changes, it still changes. Here's gold. And it's also followed by gamma. Now, it's not always followed by gamma. You will know when it's gamma emission because I will indicate it in the problem. So let's go through balancing nuclear reactions. Balance the following nuclear equation and indicate the type of decay. So here's how we do this. We want to take our top numbers, and we're going to make an equation out of it. And so we start writing 238. We're going to go ahead and the arrow will be like an equal sign. So where it has the arrow sign, we're going to put equals 234. And where it says plus sign, we're going to do a plus sign as well. This is blank, so we'll do x plus 0. Well, if we do this, what is x? X is equal to 4. So that's what we'll put in here. Next, we'll take the bottom part of our nuclear reaction. So in this case, we have 92 equals 90 plus y plus 0. So what is y? Y is equal to 2. And you should be able to recognize this symbol here. It's 4,2 helium or 4,2 alpha. And that's how you complete it. So you'll notice that the mass numbers will be equal from the reactant to product side, and the mass numbers will be equal from the reactant to the product side. Let's take a look at another example. Write the equation for the alpha decay of americium-241. So we need to actually find americium on our periodic table, and americium is number 95. Americium-241, number 95. and it goes through alpha decay. So alpha decay is on the right side of our arrow where the product side is. And alpha is again represented by 4,2 helium. And then we would do the same steps as what we did in the previous problem. We're going to go ahead and take the top numbers and find the top number here. And then we're going to take the bottom numbers and find the bottom number here, and then we'll be able to find our symbol. So on top, we have 237. On the bottom, we have 93. And look up number 93 on the periodic table. We have Neptunium. Let's go ahead and do the next example. Write an equation for the beta decay of iodine 131. So iodine on the periodic table is number 53. It goes through beta decay, and beta decay is represented by an electron. And we're going to go ahead and do the math. So the top will be 131, and the bottom will be 54. And look up number 54 on the periodic table, and we have xenon. Now make sure to double check your work, right? Because 131 plus 0 will equal 131. 54 minus 1 will equal 53. Go and try examples 4 and 5 on your own. Pause the video here and play when you're ready. So here's what you should have written down for the nuclear equations for numbers 4 and 5. I tried to show you the electron symbol in two different ways. Here we have it with the E symbol, and down here we have it with the beta symbol. And again, electron capture means that because the electron is being captured, it should be shown on the left side of the arrow where the reactants are. For the positron emission, remember that's an electron, however, it is a positive charge, and again shown after the arrow there. So let's talk about nuclear fusion and nuclear fission. I'm sure these are two words that you've heard before, especially from your history class. So nuclear fusion and fission are two different types of energy-releasing reactions in which energy is released from high-powered atomic bonds between the particles within the nucleus, which collectively, together, they are called nucleons. They produce a lot more energy compared to the chemical reactions that we'll talk about for the rest of this year. So in nuclear fission, atoms split apart to form smaller atoms, releasing energy. And nuclear power plants around the country use this type of energy to produce electricity. We have this in Virginia. We use nuclear power plants in Virginia. Nuclear fission does not occur naturally. It takes very little energy to split the atoms, and it creates a chain reaction. The downside is that many highly radioactive substances are produced as nuclear waste. The energy produced is less than fusion. We have used this as a nuclear weapon, the atomic bomb in World War II. Other examples also include the Chernobyl disaster in Ukraine and the Fukushima power plant. And also submarine engines use nuclear fission. In nuclear fusion, energy is released when atoms are combined or fused together to form a larger atom. It's a lot of energy that's involved. In fact, the energy produced is 4 times greater than nuclear fission. It takes a huge amount of energy to fuse atoms. It occurs naturally in stars, and we have used it to produce the hydrogen bomb. However, the hydrogen bomb was never used.